Since humanity first gazed upon the starry sky, we have been pondering an ancient question: are we alone in the universe? On October 19, 2017, this question received its first concrete answer. That day, the Pan-STARRS telescope in Hawaii captured an interstellar object named ʻOumuamua, meaning messenger from afar in Hawaiian. Oumuamua's arrival shattered the solar system's tranquility. Its peculiar cigar-shaped form and anomalous non-gravitational acceleration sparked years of debate within the scientific community. Some speculated it might be an artifact of extraterrestrial civilizations, but mainstream science ultimately classified it as a natural celestial body. Though many mysteries remain unsolved, the shockwaves from ʻOumuamua have yet to subside when an even more astonishing discovery followed. This is the protagonist of our story today. Triple-eyed Atlas. Unlike ʻOumuamua's fleeting glimpse, Triple-eyed Atlas's behavioral patterns have completely overturned our understanding of astrophysics. It is not merely a transient visitor to our solar system. Evidence strongly suggests it is consciously altering its trajectory, preparing for a prolonged stay in our home. This discovery is so profound that it compels us to re-examine our place within the cosmos. The behavior of this interstellar object challenges the laws of celestial mechanics established over centuries. While most celestial bodies follow gravity-dominated trajectories, Tri-eyed Atlas demonstrates autonomous control. This compels us to ponder: are we witnessing a coincidence of nature or the manifestation of some intelligent will? In the following analysis, we will gradually unravel this interstellar mystery based on observational data from multiple global observatories to gradually unveil the mysteries of this interstellar enigma. We will begin with the fundamentals of orbital mechanics to ensure every viewer can grasp this extraordinary event. We will then delve into its anomalous velocity variations and explore potential propulsion mechanisms. Finally, we will carefully consider the implications of this discovery for human civilization as a whole. Remember, the essence of scientific exploration lies in maintaining an open mind while upholding rigorous verification. We will not jump to conclusions nor overlook any plausible explanation. Whatever the ultimate answer may be, this will stand as a significant milestone in humanity's understanding of the cosmos. Now let us embark on this journey of discovery, beginning with the fundamental question: what defines an interstellar object? And contemplating a query that may alter humanity's destiny. When an interstellar visitor chooses to linger, are we prepared? The following chapters will dissect every scientific detail of this unprecedented astronomical event. To grasp the extraordinary nature of Three-eyed Atlas's behavior, we must first master the fundamental laws governing celestial motion within our solar system. The ancient discipline of celestial mechanics provides a robust framework for analyzing all astronomical movements. From Newton's law of universal gravitation to Einstein's general relativity, our tools for calculating planetary, satellite, and cometary trajectories have reached extraordinary precision. It is precisely upon this solid scientific foundation that the anomaly of the Three-eyed Atlas becomes so strikingly prominent and impossible to ignore. Every interstellar object entering the solar system carries its initial velocity from its home star system. When this velocity combines with its position within the sun's gravitational field, it determines its trajectory. For the vast majority of interstellar visitors, their velocity is sufficient to propel them along an open hyperbolic orbit. This is akin to a one-way ticket, sending them straight into the infinite interstellar void after rounding the sun. This is one of the most fundamental predictions in celestial mechanics and aligns with our past observations of all interstellar objects. The core parameter for determining whether an object follows a hyperbolic trajectory is its excess velocity. Excess velocity refers to the difference between an object's speed relative to the sun and the escape velocity required to break free from the sun's gravitational pull at its current position. A body with positive escape velocity will ultimately leave the solar system, while zero escape velocity means it will be captured by the sun's gravity and enter a closed elliptical orbit. When Triple-eyed Atlas entered the inner solar system, it indeed carried significant positive escape velocity. According to all classical models' predictions, it should have departed along a smooth, hyperbolic trajectory. However, tracking data from multiple independent observatories worldwide painted a starkly different picture. NASA's Jet Propulsion Laboratory, the European Space Agency's Space Situational Awareness Network, and the Large Synoptic Survey Telescope in Chile all reported similar data sequences. Over the past several weeks, Triad Atlas's velocity relative to the Sun has been steadily and consistently decreasing. This pattern of data variation is highly consistent across all observing institutions, significantly reducing the possibility of systematic observational error. Let us examine the specific data. Approximately 11 Earth days ago, tracking data indicated Atlas 3's excess velocity was approximately 42 kilometers per second, a notably high value, confirming its hyperbolic escape trajectory. However, 8 days ago, this value decreased to 31 kilometers per second, further dropping to 19 kilometers per second 5 days later. And the latest observations indicate its current excess velocity is only about 14 kilometers per second. This change is not random, but exhibits a surprisingly linear decay trend. If this velocity decay trend continues at the currently observed rate, simple mathematical extrapolation points to a startling conclusion. Approximately 18 Earth days from now, Triad Atlas's excess velocity will drop to zero. Zero excess velocity is a critical threshold. A fundamental transformation will occur from this moment on. The object will no longer possess the ability to escape the Sun's gravitational bonds. It will transition from an interstellar visitor to a permanent resident of the solar system, firmly anchored by gravity in a closed orbit. Orbital dynamics specialists at the Jet Propulsion Laboratory have calculated its expected orbital parameters after capture based on the current deceleration curve. According to their model, Triad Atlas will enter an elliptical orbit, with its aphelion approximately 15 astronomical units from the Sun and its perihelion nearing 0.9 astronomical units. 1 astronomical unit roughly equals the average distance between Earth and the Sun. This means its orbit will penetrate deep into the inner asteroid belt and intersect with Earth's orbital path. More noteworthy is the resonance relationship between its orbital period and Earth's preliminary calculations indicate the orbital period of Triad Atlas may form a simple integer ratio with Earth's orbital period, such as a 1:2 or 2:3 resonance. This is no coincidence. From an engineering perspective, such orbital design implies the object will return periodically to Earth's vicinity with predictable regularity, offering an exceptional opportunity for sustained close-range observation. What we face appears not a random natural process, but a precisely calculated orbital insertion maneuver. All these calculations are grounded in decades of proven orbital mechanics principles. The Jet Propulsion Laboratory possesses unparalleled expertise in interplanetary navigation. From Voyager's journey to the edge of the solar system to Curiosity's precision landing on Mars, their trajectory calculations have never deviated significantly. Therefore, when they concluded based on consistent observational data that the Triad Atlas will be captured, the entire scientific community must accord it the highest level of attention. Data is objective. Mathematical derivations yield unambiguous results. An interstellar object is actively breaking before our eyes, preparing to remain within our solar system. This fact demands deeper investigation. Faced with the indisputable deceleration of the Triad Atlas, the scientific community's primary task is to uncover its underlying physical mechanism. We must adhere to the fundamental principles of scientific inquiry. First, exhaust all possible natural explanations. Only when natural explanations fail to perfectly align with observational data should we cautiously consider other non-natural possibilities. This principle serves as our vital defense against subjective conjecture, preserving objective rationality. The first classical natural explanation considered is solar radiation pressure. All objects exposed to sunlight experience a minute thrust from photons. For objects with vast surface areas and extremely low mass, such as the dust tails of comets, this effect can indeed produce measurable velocity changes. However, calculations indicate that to generate the enormous velocity change observed in Triad Atlas, its mass density would need to be incredibly low. It would require a giant porous structure with a density close to air. Such a structure would struggle to maintain mechanical stability without disintegrating when subjected to solar tidal forces and its own rotation. Furthermore, acceleration due to radiation pressure decreases with the square of the distance, making it difficult to explain the sustained and linear deceleration curve. The second natural mechanism explored in depth is outgassing of volatiles, a typical mechanism for cometary deceleration or acceleration. As a comet's icy nucleus approaches the Sun, volatile substances on its surface, such as ice and water ice, sublimate under heat. The ejected gases act like feeble rocket engines that could alter the comet's trajectory. However, to generate velocity increments of tens of kilometers per second, Trispica Atlas would need to contain astronomical quantities of volatiles. Its outgassing activity would have to be exceptionally intense, sufficient to form a vast, luminous coma and tail. Yet across the entire electromagnetic spectrum, from optical to infrared to radio bands, no characteristic signals of outgassing were detected. No emission lines of common cometary molecules like cyanide or hydroxyl were observed, nor was any dust cloud detected surrounding its nucleus. It consistently appeared as a point-like object. This directly contradicts the hypothesis of violent outgassing. A third possibility is an encounter with an unknown gravitational disturbance. Perhaps it experienced a close encounter with an unobserved minor body. However, a comprehensive survey of its orbital vicinity at the time ruled out the presence of any sufficiently massive object. The gravitational influence of major bodies within the solar system had already been precisely calculated and excluded. The probability of such a systematic error occurring simultaneously using different methodologies and data sources is exceedingly improbable. After scrutinizing each of these natural explanations, we find they all face insurmountable observational hurdles, either failing to provide sufficient energy or producing predictions inconsistent with observed electromagnetic spectrum features or conflicting with the physical stability requirements of celestial bodies. This does not mean natural explanations are absolutely impossible, but their likelihood is diminishing. It is precisely this collective failure of natural explanations that compels us to adopt a more open-minded approach and consider a possibility we have never before confronted, that this deceleration is the product of some form of technology. Analyzing this deceleration from an engineering perspective reveals astonishing technological implications. First, consider the total velocity change, delta v. To transition the three-eyed Atlas from its initial hyperbolic trajectory to its currently predicted captive orbit requires eliminating approximately 4 kilometers per second of excess velocity. The significance of this figure demands comparison for full appreciation. The most powerful rocket in human history, the Saturn V, which launched Apollo spacecraft to the Moon, required a velocity increment of roughly 3 kilometers per second. This means the orbital maneuver capability demonstrated by the three-eyed Atlas exceeds the energy required to send humans to the Moon, and this represents only part of its changes over the past few weeks. Even more extraordinary is the propulsion's sustained duration and efficiency. Human chemical rocket propulsion is brief and explosive. A mission's primary velocity increment is typically achieved within minutes, yet the three-eyed Atlas's deceleration persisted for weeks, smooth and uniform. This suggests a propulsion system possessing extremely high specific impulse. Specific impulse measures propellant efficiency. Higher values indicate greater efficiency. This steady thrust output pattern more closely resembles theoretical fusion propulsion or advanced field-based propulsion concepts than any chemical or electric propulsion technology currently available. Particularly perplexing to engineers is the complete absence of detectable visible signals associated with the propulsion system. Traditional propulsion methods, whether chemical rockets or electric propulsion, involve the ejection of propellants and the violent release of energy, typically accompanied by distinct plasma plumes, intense thermal radiation, or specific electromagnetic emissions. Yet monitoring of the three-eyed Atlas reveals complete silence. No anomalous thermal signatures detected, no spectral evidence of ejected matter, and no associated radio emissions. It appears to exchange momentum with its surroundings in ways beyond our current perception. This may involve physical principles we have yet to fully comprehend, such as extracting energy directly from the fabric of space-time or efficiently radiating gravitational waves. This propulsion method, without a medium or apparent energy emission, if confirmed, would represent a revolution in physics and engineering. Its technological maturity clearly transcends our current capabilities by several orders of magnitude. We are not facing an incremental technological improvement, but a fundamental paradigm shift. In summary, while natural mechanisms cannot be entirely ruled out, they all face severe observational challenges. The technological hypothesis, though extraordinary, offers a more elegant explanation for all observed characteristics. Sustained deceleration, massive velocity change, high-efficiency propulsion, and most critically, complete electromagnetic silence across all wavelengths. Occam's razor instructs us to favor the simplest hypothesis among competing explanations. Yet when all hypotheses require introducing entirely new physical phenomena, the one that harmonizes best with existing physical frameworks and explains more observational facts often proves more compelling. At this stage, the scientific inference that the deceleration of the three-eyed atlas stems from a highly advanced technological artifact currently aligns most closely with observational data. This is not a hasty conclusion, but the most reasonable inference drawn from existing evidence and rigorous logical analysis. This inference inevitably leads us to contemplate a deeper question. What purpose drives this technological behavior? As the three-eyed atlas's deceleration increasingly points toward technological control, a question deeper than physical mechanisms unavoidably surfaces before us, that is, intent. Why expend such immense energy to alter its natural trajectory and choose to remain near our solar system? Understanding intent is far more challenging than understanding mechanisms because we cannot directly access its internal decision-making processes. Yet we are not without clues. We can construct a series of plausible scientific hypotheses combined with human logic and strategies in cosmic exploration to construct a series of plausible scientific hypotheses. These hypotheses are not wild fantasies, but rigorous speculations grounded in observational facts and logical reasoning. The first hypothesis is a scientific exploration mission. This represents the most direct and easily comprehensible motivation. Humans follow identical logic when probing our solar system. When launching probes to Mars, we do not settle for a single flyby. We place the probe into Martian orbit to conduct years of orbital observation before potentially attempting a landing. From a scientific perspective, the data obtainable from a brief flyby cannot compare in depth or breadth to that gathered during a prolonged stay. After completing its most recent Earth flyby, Tri-eyed Atlas immediately initiated deceleration procedures. The timing of this action strongly suggests its decision was based on new data acquired during close-range reconnaissance. It may have uncovered Earth's extraordinary complexity as a celestial body, its active geological structures, its water-rich surface, and most significantly, the presence of strong and anomalous biological and technological signatures within its atmosphere. From the non-equilibrium chemistry of methane and oxygen, to the dazzling artificial lights illuminating continental plates at night, to intricate radio signal leaks. All these point to one conclusion: Earth is a planet harboring life and a primitive technological civilization. For a scientific expedition, no discovery could be more exhilarating. Thus, altering the original plan to upgrade the flyby mission into a long-term orbital residency was a perfectly logical decision. Its meticulously calculated resonant orbit ensures it can repeatedly scan Earth from varying angles and seasons at fixed intervals. Much like a geologist camping beside an outcrop preparing for long-term meticulous documentation. The second hypothesis is the relay station and outpost hypothesis. This theory views the three-eyed atlas as part of a larger system rather than an isolated probe. When conducting deep space exploration, humans also establish relay networks, such as deploying relay satellites in Mars orbit to ensure uninterrupted communication between ground rovers and Earth. If the three-eyed atlas originates from a distant civilization, it would likely require a stable platform to report information to its homeworld or other nodes in a galactic network. Directly transmitting signals back to a homeworld light years away demands immense energy and extreme pointing precision. Establishing a relay station within the solar system greatly reduces communication complexity and energy expenditure. Furthermore, as an outpost monitoring station, its function extends beyond data relay to encompass continuous surveillance of the target, recording every technological footprint of Earth's civilization, every major space launch, every nuclear weapons test. Even overall shifts in global internet data traffic could be faithfully documented and reported. Its existence signifies Earth's civilization has been formally added to an unknown interstellar monitoring roster. Our developmental trajectory will be tracked and evaluated long-term. The third hypothesis involves a pre-contact waiting protocol. This hypothesis involves a potential interstellar civilizational interaction ethic or strategy. Direct contact with a developing civilization may be considered a highly risky endeavor, potentially causing cultural shock, technological contamination, or unpredictable conflict. Therefore, a responsible advanced civilization might adopt a more cautious, step-by-step strategy. The first step would be deploying an unmanned probe to establish presence while maintaining distance. This action itself sends a powerful signal, silently declaring, "We know you exist. We are observing your response." The three-eyed atlas stands like a calling card placed upon the threshold of our universe, awaiting our maturity to comprehend its presence and respond proactively. Or perhaps it waits for us to reach certain technological or societal thresholds, such as achieving controlled nuclear fusion, successfully colonizing Mars, or forming a unified Earth government. Until then, it remains silent, merely an observer and proof of existence. Its orbit is designed for resonance, ensuring it will remain a predictable presence in our skies for centuries to come, a constant reminder that our universe is not empty. The fourth hypothesis is the risk assessment and management hypothesis. This hypothesis takes a more serious tone, approaching the matter from the perspective of a civilization safeguarding its own security. It posits that a civilization capable of interstellar travel would inevitably remain vigilant against potential threats in the cosmos. A civilization possessing nuclear energy, intense internal competition, and accelerating technological development such as human civilization is likely to be classified as a potential unstable factor or long-term threat. Viewing Earth from the perspective of the three-eyed atlas, it may record traces of nuclear tests in our atmosphere, monitor the increasing space debris and military satellites in our orbit, analyze the geopolitical tensions permeating our international news. All these data points could collectively indicate a civilization not yet mature, yet possessing devastating power and internally fraught with tension. For such a civilization, the most prudent course is neither contact nor disregard, but sustained, close monitoring. The lingering presence of the three-eyed atlas may represent the initial phase of a risk assessment protocol, aimed at gathering sufficient data to predict the trajectory of human civilization. Whether it evolves into a peaceful spacefaring society, or descends into self-annihilation, or becomes an aggressive expansionist force, its very existence may serve as a deterrent and control measure, ensuring this potential threat remains under constant surveillance. The fifth hypothesis is the resource and preparation platform hypothesis. This is the boldest yet most compelling possibility. The stay may be a prelude to more substantive future actions. When an interstellar civilization plans long-term development or colonization of a galaxy, it first needs to establish a foothold. Tri-eyed Atlas may be executing such a mission. Its chosen orbit not only facilitates Earth observation, but may also position it near the asteroid belt, rich in mineral and water ice resources. Its primary mission could be resource exploration, assessing the developmental value of various celestial bodies within the solar system. Simultaneously, it may function as a multifunctional platform capable of self-replication or manufacturing. In the future, it could serve as a core for expanding larger structures or act as a rendezvous point awaiting the arrival of subsequent larger motherships. If its ultimate goal is to interact with humanity, whether amicably or hostilely, securing a strategically advantageous orbital position is a prudent strategic move, granting maximum flexibility and initiative for all its future operations. Having examined these 5 primary hypotheses, we must maintain clear-eyed recognition that no conclusive evidence currently exists to either confirm or disprove any of them. Together, they constitute a plausible hypothetical space. The scientific research and relay station hypotheses are the most conservative and align closest with human behavioral logic. The pre-contact hypothesis carries greater ethical implications, while the risk management and resource platform hypotheses touch upon the strategic level of civilizational survival. The true intent of the three-eyed atlas likely lies somewhere between these hypotheses or rests upon complex motivations beyond the reach of our current imagination. Our sole course of action at present is to continue observing, gathering more data on its behavioral patterns, and attempting to predict its next possible actions within the frameworks of these hypotheses. Regardless of its ultimate purpose, its presence has unilaterally altered humanity's standing in the cosmos. We have transitioned from solitary observers to subjects under observation. This shift in identity will profoundly shape the future of our civilization.